morning. This is P. Venkata Mahesh, Assistant Professor in Mechanical Engineering Department, Institute of Aeronautical Engineering. We were discussing one subject which is Applied Thermodynamics for 4th semester Mechanical Engineering students, and the topic that we have discussed previously was Vapor Compression Refrigeration Cycle. Now, as we have already discussed, we have two types of cycles. One is air refrigeration cycle and the other one is vapor compression refrigeration cycle, and the third one is the modified version of vapor compression refrigeration cycle. It is vapor absorption refrigeration cycle. Now, we in last few classes we were discussing about vapor compression refrigeration cycle, and this is the cycle that we have seen. This is the ideal cycle where the fluid at the inlet of the compressor is at a saturated vapor state, and the fluid at the inlet of the evaporator in the expansion valve. This is expansion process, and at the entrance of the expansion valve, the fluid is at saturated liquid condition. Okay, but this ideal case may not be possible in real time experience. Now, what are the different reasons why it is deviating from the ideal one to this actual one? So, this is the temperature versus entropy TS diagram, and this is pressure versus enthalpy pH diagram for the same actual vapor compression refrigeration cycle. Now, here why it is deviating? Because the fluid is flowing through pipes, so there will be some pressure drop, and because of friction and various other reasons, and because of the change in temperatures, the surrounding temperatures and the temperature of the valve or the temperature of the pipe or the compressor, all these equipment, because of this temperature difference, it will not follow the isentropic actual process wherein the temperature should be constant, but here the temperature exchange will be there. Ideally, the equipment should be isolated from the surroundings so that there is no temperature exchange between the compressor and the surroundings. But in actual case, there is a temperature exchange. Heat exchange will be there because of the temperature difference. So that is one reason. And you can see here, as I said, it is not, here you can see this is isentropic process, but here it is not an isentropic process because of the change in exchange of heat because of the temperature difference. And the other one is, here you can see the evaporator and the incoming gases from the evaporator and the cylinder walls. Okay, this is evaporator, and this fluid is flowing through this evaporator, and here it ends as the saturated vapor, but here already it is being working in condition. So what happens is the temperature of the fluid will be less than the temperature of the cylinder walls. Because of that, there will be some superheating. So and here already some cooling is happening, and because of that there can be a subcooling. So these are different reasons why the actual the ideal vapor compression refrigeration system is not possible, and how this actual vapor compression refrigeration system is coming into picture, that we will see step by step. So from 4 to 1 is our evaporation process, where the refrigeration effect is developed by taking heat from the refrigeration space. Now here what is happening, ideally it should be a constant pressure process, and at this point, at point 1, we will start at point 1, which is supposed to be a saturated vapor condition. Now here that is represented by 1D, that is saturated vapor condition. But before entering the compressor, this is the point 1 where it is entering the compressor. So before entering the compressor, it is undergoing 1, 2, 3, 4 changes. So what are these 4 changes? From 1D to 1C. So from 1D to 1C, what is happening is, because there is a lot of heat that is already existing at the inlet of the compressor walls are hotter than the incoming fluid, incoming vapor. So what happens is, the vapor is becoming superheated. Superheated in the sense the temperature, the pressure is same, but the temperature is increasing. So it is going along this pressure line. So from 1D to 1C, so what is happening is, some more heat is getting added to the vapor and it is becoming a superheated vapor. Now from 1C to 1B. So 1C to 1B, again some heat gain and superheating is happening, where in the suction line, so there is this is the evaporator and this is the compressor. So from evaporator to compressor, there is one line. There is a pipeline connected. So in this pipeline, because of the existing hotter conditions, what is happening is that heat is given to this vapor, and because of that heat addition, the temperature of the vapor is getting increased further. So this from 4 to 1D, it is in the evaporator, and in evaporator again there is some superheating from 1D to 1C, and in the suction line, that is the line between the evaporator and the compressor, there is some further superheating, that is from 1C to 1B. So there is a superheating. So what else is there in the suction line? Now in suction line, what is happening is, because of pressure, it is a pipe, simple pipe, and it is not a perfectly smooth pipe. So there will be some friction, and because of that friction, there is a pressure drop inside the suction line. Okay, inside the suction line. So because of that, what is happening? The pressure, instead of it is on 1.1B, the pressure is coming to 1A. Okay, there is a pressure drop because of the friction in the suction line. Now you can see here the pressure between 1A and 1. 1 is the actual pressure which it is entering the compressor, but at the inlet of the compressor there is a valve. Okay, at the this is a compressor. Okay, reciprocating compressor, and here is our valve. Okay, now because of reduced area, okay, here the area is reduced because of this valve. Okay, this is the pipe that is connecting the evaporator and the compressor, and at the junction we have a valve, so that the fluid is allowed only at some particular point of time. So that is the suction valve, and at the suction valve, what is happening is, the area is reduced or restricted. So because of that, what is happening, there is something called wire drawing effect. Okay, so wire drawing effect, because of this restriction in area, the fluid or the vapor of the refrigerant, which is in the form of vapor, experiences an effect called wire drawing effect, and because of this there is a little bit pressure drop, and that pressure drop is shown here as 1A to 1. So there are two pressure drops, one in the suction line and one at the suction valve of the compressor, and that is due to the wire drawing effect that is experienced by the fluid which is entering the compressor through this suction valve. So this is at the inlet of the compressor. Now what is happening inside the compressor? So the inside the compressor, it is supposed to not exchange any heat with the surroundings, but it is not possible to insulate completely. The compressor cannot be insulated completely, so there will be some heat transfer to the surroundings. Because of that, what is happening is, instead of isentropic process from 1 to 2, the path it is taking is a polytropic process. So this is a polytropic compression process, which is not a reversible process. The isentropic process is a reversible process, but the polytropic process is not a reversible process. Okay. So that is one deviation of the process which is happening inside the reciprocating compressor of the vapor compression refrigeration cycle. Now what is happening at the exit of the compressor? Inlet we have seen there are two superheating cases, possibilities of superheating. There are two possibilities of pressure drop. Now at the exit of the compressor, if you see, so what is happening from 2 to 2A. So this is the exit of the compressor, pressure is higher, and this is the inlet of the condenser, and between these two there is a pressure drop, two pressure drops. One is 2 to 2A. So what is this 2 to 2A? Similar to the suction line. Similar to the suction line that we have between the evaporator and the compressor, we have a delivery line or discharge line between the compressor and the condenser, and also we have a discharge valve. So this is the discharge line, and we have a valve here at the inlet of the at the exit of the compressor. We have a valve. Say suppose this is the compressor, we have two valves here, one is like this, the other one is like this. So this is the suction valve, suction line and suction valve, and this is the discharge valve, and this is the discharge line. Now here again at the discharge valve, what is happening? The area is again getting reduced because of the presence of the valve, and because of that the fluid experiences again a wire drawing effect, and there will be a pressure drop. So at the suction valve and the discharge valve there is a pressure drop. Now as I discussed here, this is the discharge line or the delivery line. So in the delivery line again we have a pressure drop. So this is the suction line and this is the discharge line. So the discharge line is connecting the compressor and the condenser, and the suction line is connecting the evaporator and the compressor. So here again, because of the friction, there is a pressure drop in the discharge line or delivery line. So that is represented by 2A to 2B. Okay, 2A to 2B is representing the pressure drop in the discharge line, and 2 to 2A is representing the pressure drop at the discharge valve because of the wire drawing effect. Now what is the other one? There is a point 2B and point 2C. So what is happening here? So what is happening here is the delivery line will be at lower temperatures. Okay, the delivery line is at lower temperature. Now the fluid coming from the compressor is at higher temperature. So what is happening here? The heat is taken by the delivery line. Because of that there is some desuperheating. Increase of the temperature of the vapor is called superheating of the vapor. If the temperature of the vapor is getting reduced, then it is called desuperheating. So we have desuperheating at the in this delivery line. Okay, we have pressure drop in the delivery line, we have desuperheating in the delivery line because of the lower temperatures of the delivery line. Now what is happening here? There is a point 2B and 2B to 3, and we have already discussed it is 2B to 2C. From 2B to 2C already the pressure, the temperature got reduced. Okay, and the from 2B to 3, it is supposed to be a constant pressure process. Okay, from 2B to 3, it is supposed to be a constant pressure process, but since the condenser is also a pipe, okay, it is a pipe system, so it can be a concentric pipes like this. One fluid is flowing through the inner core, the other fluid is flowing through the outer core, and so any system can be there here. The piping system can be anything, but it is a pipe. If it is a pipe and the fluid is flowing through the pipe, there will be some friction losses. Because of that, the pressure is going to reduce. So from 2B to 3, it is not a constant pressure process. As you can see here, it is a constant pressure process in ideal case. But in actual case, what is happening is there is a pressure drop. Even if you see here also, there is a slight change in the pressure. Okay, it is not a straight line. It is having some slope. Okay. Now what? Subcooling effect of liquid in the condenser or subcooler. Okay. So here, as the process is continuously happening, what happens is, instead of giving a saturated liquid, okay, instead of giving a saturated liquid at point 3, what happens is there will be a temperature loss further inside the condenser, and that is called the subcooling of the liquid. So what is happening here? There is a subcooling effect in the condenser. Okay, and that is represented by 323A. So this is the subcooling effect. Now heat gain in the liquid line. Okay, heat gain in the liquid line. So what is this liquid line? There is a line between the condenser and the expansion valve. Okay, there is a line between the condenser and the expansion valve where the temperatures are little higher than the coming liquid which is coming from the condenser. So because of that, some heat will be added, and again from 3A to 3B there is some heat addition inside the liquid line. Now here there is a statement: the lines 3 to 3A and 3A to 3B are along the saturated liquid line on TS diagram, as the constant pressure lines in liquid region run close to it. So what is the meaning of it? So here, if I see this TS diagram, the constant pressure lines. So here this is constant pressure line, and if here the constant pressure lines are nearer, and here if you see the constant pressure lines are little farther in vapor region, but in liquid region the constant pressure lines they will be very closer. So what they are doing is they are representing on the saturated liquid line only. So this, say suppose it is like this. Okay, so since these are close to this line, instead of representing separate lines, what they are doing, they are representing the liquid lines on the same saturated liquid line. Now what is the other one? The last one is the pressure drop. There is a pressure drop in the evaporator. Why there is a pressure drop? Again, the same reason. The evaporator is also a pipe. Okay, the evaporator is also a pipe, when the fluid flows through a pipe, it definitely encounters the friction, and because of that there is a pressure drop even inside the evaporator. Now here, in case of evaporator, in addition to the friction drop, we have an additional pressure drop that is called momentum pressure drop. So what is this momentum pressure drop? So here what is happening is, from here to here, it is here it is liquid and here it is vapor. From here it is liquid, from here it is vapor. So as it is, the phase change is there, the liquid is getting converted into vapor. So the volume of the vapor is more than the volume of this liquid. Because of the increase in volume, what happens is there is a kinetic energy drop. Here there is a less volume, here it is more volume. So because of that, what is happening is it tries to oppose the flow, and because of that what happens is there is a change in volume. The volume is increasing. So the volume is increasing. So the same time it should take. More volume should be passed through the liquid in same time. Say suppose I have 1 liter and it is supposed to be transferred in 1 minute. And here the volume is more. Say suppose 10 liters. And the 10 liters also should be supposed to transfer in same 1 second, because the fluid is continuously coming. The fluid is continuously coming, and here the volume is increasing, and the same time it is having to cross this pipe. So because of that, what is happening? Same more volume is transferred in same time. So the velocity is increasing. As velocity increases, there is a pressure reduction, because it is supposed to follow the energy law of conservation of energy. So the pressure energy, the kinetic energy, the potential energy, the sum of all these energies must be constant, okay, between 2 points. So here what is happening? There is some kinetic energy gain. The increase in kinetic energy is obtained from the pressure drop, and that is called the momentum pressure drop. Now this is the pressure drop in the evaporator. So that is what I was discussing. The pressure drop is from 412 412 1D, and this pressure drop and the temperatures are given as T0, T01, T02 and P01, P02 on 2 different diagrams. Okay. Now in condenser. So in condenser also we have seen that there is a pressure drop, okay, because of the friction. Then what about the momentum pressure drop? So what is happening in here? Here it is vapor. Okay, here it is a high temperature vapor, but here it is a liquid. So what is happening? The vapor is getting condensed into liquid form. So vapor is getting condensed into liquid form means there is a reduction in volume. So reduction in volume is what happens to the kinetic energy? The kinetic energy decreases. So since the kinetic energy is decreasing, that kinetic loss in kinetic energy is added to the pressure. Okay, the loss in kinetic energy is added to the pressure. Because of that, the pressure increases, or the pressure drop is negative. In textbook it is written as pressure drop is negative. Don't get confused about it. Because of the decrease in kinetic energy, the pressure is increased in the condenser. So there is a pressure drop because friction, and there is a pressure increase because of the momentum pressure drop. So these two are compensating each other, and because of that we don't see a significant pressure drop. One, because of friction, the pressure is decreasing, and because of the change in momentum the pressure is increasing. So what is happening, one is negative, another one is positive, which is making the line is almost a straight line. So the pressure drop inside the condenser is almost insignificant because of this opposite natures of the pressure drop due to friction as well as pressure drop due to momentum. So we'll just summarize what we have discussed till now before we go to the next topic. We'll see one more small topic today and we'll close the session. So what is happening? The ideal vapor compression refrigeration cycle, if you see, from 4 to 1 it is a constant pressure process, and at 1 it should be the saturated vapor, and from 1 to 2 it is supposed to be isentropic process, and from 2 to 3 it is a constant pressure process, and at point 3 it is supposed to be saturated liquid, and from here to 3 to 4 it is a isenthalpic process. Now what is happening in actual cycle? So in actual cycle what is happening is, at the in the evaporator, because of constantly the heat is getting added, what happens is it tends to increase the temperature more than the saturated vapor, so it is becoming superheated vapor in the evaporator. And from C to B in suction line also there is some heat addition, so there is some further superheating, and in suction line there is a pressure drop due to friction, and from 1A to 1 because of the wire drawing effect in the suction valve of the compressor there is a pressure drop, and from 1 to 2 because of the heat transferred to the surroundings it is no more a isentropic process, it is becoming a polytropic process, and from 2 to 2A what is happening, there is a pressure drop at the discharge valve because of the wire drawing effect, and from 2A to 2B in the discharge line there is a pressure drop due to friction, and now from 2B to 2C there is a temperature reduction. Okay, there is a temperature reduction in the suction line. So in the suction line we have pressure drop as well as reduction in temperature. In the line between the, so this is the delivery line, this discharge line. In the suction line we have a superheating and pressure drop. In the delivery line or the discharge line we have a desuperheating or reduction in temperature as well as pressure drop. Now coming to the condenser. In condenser what we have? We have a pressure drop due to friction and the pressure increase in pressure because of the momentum, change in momentum. Okay, because of the change in momentum there is a pressure rise in condenser. Because of that the one is positive, the pressure drop because of friction is positive, the pressure drop because of the momentum is negative, so they are going to nullify each other, so there is not a significant pressure drop in the condenser. Now what is happening at the end of exit of the condenser? Because it is a continuous process, it tends to supercool the liquid, then it is supposed to be what it is supposed to be, a saturated liquid. Instead of giving a saturated liquid, it takes temperature further, so it gives a subcooled liquid. Now in the line between the condenser and the expansion valve there is some heat addition to the fluid, so because of that from 3A to 3B there is a temperature rise. Now from 3B to 4 it is a expansion process which is an enthalpic process, constant enthalpy process, isenthalpic process or constant enthalpy process. And from 4 to 1D, we have two pressure drops. Here one is positive and one is negative. Now in this here, if one is the pressure drop due to friction is positive, as well as the pressure drop due to change in momentum is also positive. So there is a lot of pressure drop between 4 and 1D. But if you see from 2 to 3, the pressure drop is almost insignificant. So this is about the actual vapor compression cycle, how it is deviating from the ideal vapor compression refrigeration cycle. Now, in next class what we'll do, we'll try to analyze the vapor compression refrigeration cycle. So before that, we need to understand one term which is called ton and tunny. Okay, so this is a ton and this is some people call it as a tunny. And what is this ton? It is a American unit of weight. So ton is an American unit of weight, and ton is equal to 2000 pounds, and this is equal to 907.185 kg. Now what is this tunny? It is the metric ton, and that is equal to 1000 kgs, and the metric ton is equal to 1000 kgs. So tunny is 1000 kgs, TON ton is 2000 pounds. So it is 1 ton is equal to 0.9 tunny. Okay. Now why we have to discuss this? So there is something called ton of refrigeration or unit of refrigeration capacity. So just like we have weight, units for weight, pressure, density, all those things, we also have a unit for representing the refrigeration capacity of a refrigeration plant. Now that refrigeration capacity is given by the ton of refrigeration. In America, they use the ton of refrigeration, TON, ton of refrigeration, and it is represented by TR. Now what is this 1 ton of refrigeration? So 1 ton of refrigeration means we are taking 1 ton of water. Okay, we are taking 1 ton of water, and at 0 degrees centigrade we are converting this from into ice. So that is one way. The other way is that is we are adding the latent heat. So but what is refrigeration? We have to supply the cooling effect. So what we can do? We take a 1 ton of ice or 2000 pounds of ice we will take at 0 degrees centigrade. Now at 0 degrees centigrade, the ice is, if we leave this ice, what happens? It will become water at 0 degrees centigrade. So the water at 0 degrees centigrade, if the total 1 ton of ice, okay, in 24 hours, how much heat how much cooling effect it can produce by melting from ice to water at 0 degrees centigrade, that is called the 1 ton of refrigeration. So what is 1 ton of refrigeration? We are taking 1 ton, TON ton, or 2000 pounds of ice at 0 degrees centigrade, and we are allowing it to melt, and the process it supplies some cooling effect in 24 hours. Okay, so that cooling effect is termed as 1 ton of refrigeration, or simply TR. So what is the value of it? So the weight is 907.185 kgs. So that is 1 ton, and the latent heat of ice, latent heat of melting of ice is 334 kg. Okay, 334 kilojoules per kg. So, and what is the time? It is 24 hours. 24 hours, if I convert into seconds, it is 3600 seconds. So the net value is 3.5 kilojoule per second. So 1 TR, 1 TON ton of refrigeration is 3.5 kilojoule per second. In terms of minute, if I want to say, it is 210 kilojoule per minute. In hours, if I want to say, it is 126000 kilojoule per hour. Now what about the ton of refrigeration? Now the commercial people, they in India, they use the ton of refrigeration. So what is that? 1 ton is 1000 kilos of water or ice. Okay, 1000 kilos of ice we are taking, and in 24 hours the 1000 kilos of ice is getting melted from 0 degrees ice to 0 degrees water. Okay, we're keeping the temperature constant 0 degrees centigrade, but if before starting it is completely ice, after 24 hours it is completely water. So during that process, how much of latent heat of ice it is absorbing, that is called the ton of refrigeration. Now what is the value of this ton of refrigeration? 1000 kgs of ice we are taking, and the latent heat is 334 kilojoule per kg, and 24 hours and in seconds it is 3600. So the value is 3.87 kilojoule per second. Now if I want to convert that into minutes, it is 232 kilojoule per minute. And now what is it in hours is 13917 kilojoule per hour. So as I already said, 1 ton of refrigeration is equal to 0.9 ton of refrigeration. So this is about the units of refrigeration. We have 2 units of refrigeration. One is the American system, that is a TON of refrigeration. The other one is metric system, and that is equal to ton. 1 ton is 1000. Okay, 1 ton when you are using 1000 kgs of water, 1 TON when you are using 900 something kgs of ice. So that is about the units of refrigeration. With that, I am closing the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.